Hi everybody. So I am Sebastien. I am a co-founder and VP engineering of Hopper. So at Hopper we're building a search engine for travel. So in the beginning there was an idea. So why isn't there a good tool for planning a trip online? I mean, there's information about places scattered over the web, on blogs, on articles, on trip journals, etc. Assembling all of that information is actually a lot of work, right? So booking a flight is not actually the problem. What if I don't even know where I should go? So we set about to build the world's largest structured database of travel information, which we soon discovered would be a really big database. So this is where the fun began. So my presentation today is about telling you a little bit about my personal experience with combining a startup with NoSQL and a search engine together. So most of the time it's like the lady's face, but sometimes it's more like the guy's face. Alright, so what makes it a roller coaster? Well, first of all, it's a startup, and as anybody in a startup will testify, there are ups and downs. And second, turns out that building a search engine is really damn hard. So one problem with a search engine is that all the scalability issues that you're getting normally when you're in a startup as you grow your user base, it's all front loaded, because the results of a search engine will actually be irrelevant until you have a critical mass of data in your system. So that puts right. So basically, in order to solve these problems, for us, what that meant is having to deal with new big data technologies to support the amount of data, having to build our own data center, and it puts a lot of pressure on the algorithms because there's so much data and the data is so nasty. Okay, so let's start with the new big data technologies. For the processing, we're using Hadoop, which works great for us. But we also need a place to store our structured data. So that's where NoSQL comes into play and things start to break down. So back in 2007, we were using HBase. So back in 2007, HBase, not so great. So we had data corruption every single week. We lost the database so many times. Data was often not available. The deleted rows were actually coming back by magic. Like, what? It was a mess. So we switched to Cassandra. At first, it proved to be a more stable solution than HBase. We were actually able to load our biggest table, so that crawled pages, without having it crashing. So it was actually a big move for us. It was a big step forward. But then we had bad surprises. So it turns out that Cassandra is terrible with scans, which is kind of wrong when you're doing MapReduce. And also the garbage collection is crap. I don't know what they're doing with their memory, with their objects, but I don't know, it's terrible.
Sorry, when you say it's terrible with scans, could you be more specific?
Right, so Cassandra is eventually consistent. It's a little bit like what you guys have in Mongo in terms of, it's eventually consistent in the sense that you write your data and then at some point it's going to be written on disk. And so typically what people do is that they have a column write and column read, so that let's say you have a replication factor of 3. It means that as soon as you have at least 2 servers that acknowledge that the data got written, the write is successful. And then you do the same thing on the read. As soon as you have two servers that you query all the servers, but as soon as two agree on the result, then you say, all right, it's good. The problem is that when you do that with scans, with MapReduce, you have every single, and if you want, okay, so by default, the scans, they only do a request to one server, right? So it's a consistency level of 1. That's the default for Cassandra for MapReduce. It means that if you're lucky, your data will be there, but it's not guaranteed. So in our case, we cannot afford that. We cannot afford that sometimes the United States won't be there, right? So in order to avoid that, we have to have a reconsistency of quorum, which means that during the scan, each server is not only talking to itself, but to the replicas as well. And then guess what? So if you have a replication factor of 3, it means that it puts three times more load on each server. So it was crapping out. All the disks were saturated. It was basically exploding. So all the servers were in red. So figure it's not for us.
So just to clarify, when you say a scan, you were looking, you were trying to iterate over all the keys in a column family?
Yes.
Okay.
Yes. So it's for it's when you do MapReduce, usually you just go through all of your data set, right? But if you do quorum read like this, it's as if you go through all of your data set 3 times. So that's problematic. So it didn't really work out for us. So we went back to HBase. In HBase, the reason why it works for us, to follow the previous question, is the fact that there's only one server that you can read and write. It can write and read. So, when you do that right, you know for a fact that your data got written, so you don't lose data. And when you read, well, that server needs to be up. And if it's down, it's going to be the data that it's responsible for will be reassigned to another server. So your request will fail for some time, but then at some point you're going to get. Anyways, the bottom line is there's only one server that you need to query in order to ensure consistency, right? So when you do MapReduce jobs, what that means is you always do a request only to local host. So even if you're processing terabytes, hundreds of terabytes of data, it doesn't matter. Your network I/O will be 0, exactly 0, because everything happens locally.
So in those 4 years, did HBase got all the problems fixed?
Yeah, that's the thing. So what happened is HBase at the very beginning, they were putting a lot of emphasis on the features, but not so much on the back end. So that's why we started. Well, we started because of it had all of these functionalities. It seemed great, but then everything was failing because it was not robust. And then Facebook created Cassandra, and they were focusing at the beginning only on the back end. Feature-wise, it was like terrible. You had to do everything yourself. You want to read and write, you basically have to write your own client because it was so low level, just directly and drift. So anyway, then what happened is that while we were messing around with Cassandra, the HBase guys, actually what happened is Facebook, they dropped Cassandra like 1 month after we did the switch to Cassandra, and they took HBase instead. And then during that year, they stopped. They didn't write any feature in HBase, but they just worked really, really hard on improving its stability. And then during that time, Cassandra was doing the opposite and adding like features like crazy. So Cassandra got unstable, HBase got more stable, and then when I looked at it like a year and a half later, and it was still exactly the same features, but it was working. Yes?
When you mentioned that in HBase, all of the reads and writes are local to that one server that gives you the exact result, in that case, HBase doesn't really shard, it only replicates, does it? Because if only one server is allowed to take writes and only one server can read reads, the other ones are backups.
Right. So the replication happens not at the HBase level, but at the storage level, so in HDFS itself. So when you do a write, it writes to a file in HDFS, and they ensure that the data is located on at least 2 servers. So therefore, you're okay with that. So
wouldn't that also be the same if you set the write quorum in Cassandra to the amount of servers? It would also be.
The problem is that you're talking to more than one server. So in the case of when you do the read, so the problem is that when you do the read, right? In Cassandra, if you want to make sure that your data is consistent, you need to read on more than one node, whereas in HBase you don't need to. It's only one node, and you know that your data will be there.
But you could also just say, tell Cassandra to write on all of them, and as soon as all of them actually acknowledge that the
That's
data
what
is
we
there.
did, but then guess what? You have one node, you have a cluster of 100 nodes, one of them dies, and then all of a sudden in your cluster you cannot write to some keys anymore, because if it tries to write on the node that is dead, it doesn't work. It fails.
And how would that work in HBase with your one server that is responsible for consistency?
It's because that node is up, so you can write to it, and then somehow HDFS will replicate to all your different nodes. If the node that is responsible for a set of rows dies, the data for which it's responsible will be reassigned to other region servers.
Okay, and then you have to fail over basically. And
Well, yeah, the client handles that for us, so we don't need to worry about it. But yeah, and also in Cassandra, it's responsible for one portion of a. Well, anyway, that's a different discussion. But the fact that the way that HBase splits its data is more, it's more like by chunks. It says this range of rows is responsible. Basically, you set a table into a lot of different chunks, and these chunks, they can be moved away. They can be moved from one server to another to be the load balance, and failover, etc.
it's a Dynamo paper that basically describes that, which I think Cassandra implements.
No, it's more Cassandra. Well, Dynamo is more similar to Cassandra. Cassandra, it's responsible for, like, you split your ring into ranges, but they are giant ranges. What I'm saying is that in HBase, it's smaller chunks. It's more, since it's smaller, you can more easily balance your load in the cluster, because you have like one chunk that there's too much load on it and too much data. You can split it, and that part will be moved to somewhere else. Whereas in Cassandra, if you have one node that dies, it's kind of problematic because all of your data is there. But anyway, it's easier to grow and to control the behavior of HBase than Cassandra. When a node dies in Cassandra, it's a nightmare. It starts streaming like crazy, and then the network is not responding very well anymore. Yeah, so HBase on the path of success. So it's actually working pretty well for us. You need to configure it properly, but past that point, it's okay. So having the data is one thing. So all the software, etc., it still needs to run somewhere, right? So the hardware is important. Which hardware you choose. So there's been several iterations for us on the hardware level. So first iteration, we tried an EC2 cluster. That was in 2007. It's very appealing because it's very easy. You press a button and all of a sudden you have a cluster of several dozens of machines. It's very straightforward. The problem though is it's very expensive for 24/7 operations. EC2 is great if what you want is to grow and shrink your cluster dynamically. Let's say you have a big analytic job that needs to run on a big data set, and you spawn out the machines that you need to have the processing power required to do it, and then once you're done, you shut down the cluster or shrink it back down. The problem is that if you run it 24/7, if you do the math, it just doesn't work. It's very expensive. And it's also not really reliable. It has latency problems. Sometimes the network will stop responding, and the disk access will take several seconds before you have a reply. So it's much easier if you control the hardware yourself. Sorry? Yeah.
There's some surprise.
All right. So then we were dumb enough to try to do it ourselves. So that's V1. Actually, that's V2. Is there something worse than that? Okay, so these are components mounted on plexiglass and with Velcro, and the ventilation is ensured by the angle of those IKEA things that hold everything together. So that is awesome. Okay, so then we hired someone that actually knew what he was doing. He does this. Because there's that one thing we learned with plexiglass, it's great for static. Our motherboards kept dying. It was very cool.
Those pizza boxes like that.
The what?
Pizza boxes.
No, these are, these are, yeah, they look like pizza boxes, but they're actually some frames that we put, anyway, so that's other boards with another version that was even worse. It didn't work either. So, and then the second thing is they did this. So now it looks a bit more professional. Gotta say it's the $8 million from Atlas Venture kind of helped as well. All right, so now with all the processing power and the amount of data, even if we have all the processing power, the amount of data still puts a lot of pressure on the algorithms, right? We need to do something with it. So this is our overall data flow at Hopper, and pretty much all of it is all big data, NoSQL, MapReduce. So things relevant to go through it. So it gives you a real example, of real life what we do with it. So most of our data, we get it from web pages that we crawl, and we extract basically information from it. We extract two kinds of information. We extract entities here. Entities, for us, it means things that exist in the physical world, like a restaurant, a hotel, an attraction, a city, a river, a mountain, a rock, etc. And documents. So documents are basically web pages that talk about the entities, like an article, a review, a blog, etc. So, and the way it works is we have a team in the Philippines. There are about 25 people or so, and they find the relevant websites for travel, and once they find one, they analyze them to tell the system where the relevant information is on these websites. For example, let's say that someone, a Filipino, finds out that TripAdvisor is a great source for hotels. He'll go to TripAdvisor and annotate a few sample pages. Typically it's 3, and it's going to say, all right, here's the name, here's the address, here's the telephone number, star rating, description, pictures, etc. And then we feed these to a classifier to train it, and then basically build a model that we apply on the pages that we crawl afterwards. And then we go and crawl all of TripAdvisor. So that's how we get from a few minutes of human labor to potentially hundreds of thousands or even millions of records, right? And since it's human curated, the accuracy of this data, the quality of that data is really, really high. Something much higher than, let's say, you use an automatic information extraction algorithm that you're kind of bounded to something like 75% accuracy because of all the crap that you can find on the web. So that's how we get most of our structured data. We also get data from dumps like Wikipedia, GeoNames, etc. So that's for the extraction. So now the next problem is, let's say we found a hotel on TripAdvisor. The reality is that we're going to find that same hotel potentially on thousands of other websites, right? So what we need in the end is a clean database, a clean table of entities here, right? So what we need is to find these duplicates and somehow merge them together. So merge is actually a pretty hard problem. So the data is really messed up on the web. There's invalid data, incorrect data, missing data, everything you can think of. And somehow it needs to reconcile all that and merge the duplicates together. And if we if we unmerge, meaning that two hotels, for example, should have been merged together and that they're not, it means that you can see the same hotel twice in the results in the end, which is pretty bad. But if it's overmerged, it means that you can potentially have like a Hilton merged with a Comfort Inn, and so you can have like the address of one and the telephone number of another one. You show up to the wrong address. Not very good. Okay, so that's for the merge. So let's assume that the merge did everything properly and we have a clean database of entities, which is not necessarily the case. So the next step is to go back to the documents and analyze all the documents and try to identify what entity they're talking about. So let's say we have a review about one of the hotels we extracted from the TripAdvisor. The goal is to identify in our database which record is it talking about, right? Same thing with a blog or any other document. So like a blog about the Eiffel Tower, we need to link the blog to our entity in our database. So that's the resolution part. So once we have that, then we go and create the final index that is used by the search engine, which basically we're indexing the intersection of the entities in the documents where we found them. So the output of it is an index of entities along with all the contextual information of where we found it. So for example, going back to the Eiffel Tower, let's say we found like 100,000 pages that talk about it. We basically take the content of all these pages and inject it in the Eiffel Tower, and that makes it searchable in the end by the search engine, right? So we have the structured properties like the name, its location, its type, etc., and all this data. So that allows us to answer queries like running of the bowls. So our system knows nothing about running and nothing about bowls, but it will give Pamplona as a first result, which is a city in Spain where it's known for that. There are other places in the world where running the bowls occurs, but it's not as known as Pamplona. Yes?
The inverted index that you create for the search, do you also store that in HBase, or is it something like Lucene in the back end, or?
Yeah, it's not in HBase. That we just store, it's a Lucene index that is produced. It's temporarily goes to HDFS because it's the output of a MapReduce job, but then the resulting files, then they're moved to the index server.
And there's like a batch process, so it's like nightly, or do you actually do
Yes.
time?
So that's actually my next point. This whole thing, right? It happens every night. So the first thing that we do, actually, let's say there's going to be a run starting like in a few minutes. First thing it's going to do is delete all of this, this, and this, and basically we're dropping the whole database and recreating from scratch from the web pages here. And that happens every single night. Now, there are reasons why we keep redoing everything. It's not just because we like to.